Okay, in this lesson we're going to discuss the exponential function. Here's the way you write it. Two to the x power. That's the first one we're going to look at. And as we've done before, let's just put in some values for x and see what we get. We'll make a table over here. If x is 0, then anything to the 0 power is 1. So we're going to have 0, 1. If x is 1, then 2 to the first power, of course, is 2. If x is 2, 2 squared is 4. X is 3, 2 to the third power is 8. 4, 16, 5, 32, and so on. Of course, it's easiest to put in integers. That we could do it for non-integer values as well. Numbers like 2.136, whatever else. What about negative numbers? Negative 1, 2 to the negative first power means 1 over 2, which is 1/2. Negative 2 is going to be 2 to the negative 2, which is 1 over 2 squared, which is 1/4. Negative 3 is going to be 1/8, and so on. So if you graph those, here's what it looks like. It goes up very, very fast, and it goes down very fast, even faster than I have it indicated there. But say here's the value 1 right there. I'm going to have to cheat just to get this thing to fit on the board. There's 2. There's 3, and so on. So it goes up very fast and goes down fast. Let's compare that with the graph of y equals 2x. 2 times x. That's just a line going through the origin. We've discussed lines before. Looks like this. Here's a good way to describe, or I should say to contrast, these two functions. With this function right here, as you go from 1 to 2 to 3 to 4 and so on, you add 2 to get to the next value. Here you're right here, you add 2, and now you're there, you add 2 more, and you're right there. That's why we say the slope is 2. We add 2 more, and the slope, and you're there, and so on. Here, in contrast to adding 2, we multiply by 2. And going from here to here, this value is not 2 more, but twice as high as this value. When you go here, the value is twice as high as the previous value. You go up to 4, and the y value is twice as high as the other value. So that's kind of an interesting, an important way of contrasting these two. So that's 2 to the x, okay? What if instead of 2 to the x, we wanted to graph 3 to the x? How would that look? Let's. This is where another marker would be handy. Let's see if this one works. Very good. Y equals 3 to the x. Let's see. Well, you can kind of see pretty easily it's going to look very similar to 2 to the x, except now we're working with 3 rather than 2, so when you stick in a 0 here, you still get a 1 out. You put in a 1, you get a 3. Put in a 2, 3 squared is 9. Put in a 3, 3 cubed is 27. Put in a 4, 3 to the 4th is 81. You can put in negative 1, it's going to be 1/3. Negative 2 is 1/9, and so on. So it's going to have the same general shape as this one, it's just going to be exaggerated. So as fast as this thing went up, this one's going to go up even faster. So again, I'm not going to be able to do it to scale. It's going to go really fast. And similarly, as you put in negative numbers, it's going to go down faster. So it'll look something like that. There's no asymptote there. Maybe I better just make sure that it doesn't look like there's one. It keeps, you can put in as large of x values as you want. Oh well, that's a rough idea. By the way, I should just mention, I'll mention it right now while I think about it, that there's a great program available to you free. It's called Desmos. I love it because I'm not a tech file at all. I like things that are simple, and this, if you put in Desmos and put in free calculator, you don't have to put in your name or anything else. You just start using it, and you can just write y equals 2 to the x or 2 times x or whatever, and it's wonderful by way of giving you graphs of functions, and you can do other things with it as well. Anyway, you can get graphs of these graphs here. So that's 2 to the x. Or that's 3 to the x, rather. Now, I want to take just a little break, and this is going to lead to the next graph we're going to put on here. Get rid of this. I remember when I first got my calculator, way back when, I started playing with it, and I started playing with this question. If I took 1 and added 1/2 to it, and then squared it, how did that compare with taking 1 and adding 1/3 to it, and then cubing it? Or taking 1 plus 1/4 to the 4th power. Which of those numbers is bigger? On the one hand, this is a larger number. 1 plus 1/2 is 3/2. That's bigger than this, which is bigger than this. On the other hand, if you take any number greater than 1 and raise it to higher and higher powers, you make it bigger. So this particular number you're squaring. This number, which is smaller inside here, you're cubing it. And this number, which is still smaller, you're taking it to the 4th power. So I really got wondering what happens as you go farther and farther, and you can take 1 plus 1/10 to the 10th power, and so on. What happens to those? And it turns out that when I put them into my calculator, it turns out that as you get larger and larger and larger, 1 plus, say, 1/1000th to the 1000th power and beyond, that people could argue both ways. I should say 2 different ways. Some people think, well, these numbers must be getting closer and closer to 1, because 1 plus 1/1000th is very close to 1, and we know that 1 to any power is just still stays 1. 1 to the 1000th is still 1. So some people argued, well, this thing probably gets closer and closer to 1. On the other hand, it's also easy to argue that that is going to go off to infinity, because if you take any fixed number, like this, for example, which is fixed, and you take it to higher and higher powers, and you just go to higher and higher powers, that's going to go off to infinity. There's a symbol that stands for just becoming arbitrarily large. And that's going to be the case because, as I say, if you take any number greater than 1 and just take it to higher and higher powers, that's going to just get bigger and bigger and bigger. So you can make a pretty good argument that this thing is going to head towards 1, and you can also make a pretty good argument that this thing is going to just get arbitrarily big. And the question is, which happens? And the really cool thing that happens is neither of these. The 2 compromise. I actually wrote a paper on this whole idea, just saying that other things in life are maybe like that as well, that people want one extreme or the other, but sometimes the truth is in the middle. And in this case, go ahead and check it out on your own calculator if you want. Just put in 1 plus 1/1000th to the 1000th power or any other large number, and you'll see that you get a number pretty close to 2.718182, so on. This is a number which comes up a lot in mathematics, kind of like the number pi, and so we actually give it a name. It's an irrational number, it never stops. We give it the name E. So E stands for this unique number, which this sequence of numbers go to as you put in larger and larger values here. Okay, so it goes to the number e. I'll just let you know right now, just by way of completeness. Here's another place where e shows up. If you take the graph of 1 over x, remember what 1 over x looks like? And if you start at 1 right here, and you ask, how far do I need to go in this direction before the total area underneath this graph is equal to 1? How far do I have to move in this direction before the total area of underneath this graph is equal to 1? It turns out you have to go to that same number. If you go to e, then that's where the total area is 1. So we'll be discussing those various things as we go throughout the course. But the point is, e is this very important number, and it's between 2 and 3 in size. And so if I now look at e to the x, I get the same sort of graph as I did for these other two. And let's do that one in blue. Since e is between 2 and 3, e to the x is going to just end up right between those two. It's hard to draw it, but it's going to be between those two right there. So there's e to the x. Okay? So that's what those functions look like. Once you have those, you can get lots of other ones. So for example, let's look at y equals 2 to the negative x. Well, no, let's do 1/2 to the x. One-half to the x value. Well, one of the properties of exponents is that this can be written as 1 to the x value over 2 to the x value. And so that's just equal to 1 over 2 to the x. And so we see that as 2 to the x gets very, very big, 1 over that is going to get small. And as 2 to the x gets very, very small, 1 over a small number, as we've discussed, gets big. So 1 over 2 to the x looks like that, which is the same as 1/2 to the x. And again, if you wanted to, we could have just put in values for x here, and we would have gotten the same thing. We would have seen that it goes small there and gets large going in this direction. So those are the main ones that you need to be concerned about. 10 to the x is just another one. You can imagine what 10 to the x is going to look like. It's going to go up even faster and go down even faster. But those are all those graphs. Okay, I just mentioned one of the properties of exponents. Let's list all the properties out. There's some important ones. And we'll let a just be any positive number here. So it could be a 2 or a 3 or an e or anything else. And here's the properties. First of all, a to the x plus y is equal to a to the x times a to the y power. Okay? That's familiar to you if you just think about things you've maybe seen before. If you take 2 to the 3 plus 4, that's equal to 2 to the 3rd times 2 to the 4th. Why is that? Well, 2 to the 3 plus 4 is 2 to the 7th power. That's what that stands for. And 2 to the 3rd means 2 times 2 times 2. These are all being multiplied. And this one is also being multiplied. And so you see, since everything's being multiplied that makes sense. 2 to the 7th is 2 to the 3rd times 2 to the 4th. So this is just saying the same thing. Similarly, a to the x minus y is equal to a to the x divided by a to the y. So those two kind of go together. Another important one is that a to the x all to the y power. What's that equal to? Well, let's do an example again. If I take 2 cubed all raised to the 4th power, what does that mean? That means 2 cubed times 2 cubed times 2 cubed times 2 cubed. And now if I were to even expand this further, I've got 2, 2, 2 here, and I've got 3 more 2's here, 3 more 2's here, and 3 more 2's here, all being multiplied by each other. And so you notice I have 3, 6, 9, 12 2's all being multiplied. So this is just equal to 2 to the 12th power. So in other words, when you take a to one thing all raised to the other thing, that's a to the x times y power. So that's an important property. Let's see, anything else? I guess maybe it's important to mention, as I did before, that anything to the 0 power is defined to be 1. And I guess, let's see, what else? A to the, just to be specific about it, negative x power, that would be 0 minus x. So if you wanted to, you could write this as a to the 0 minus x power, and that's equal to, using this property, that's equal to a to the 0 power divided by a to the x power, which is 1 over a to the x. So that's kind of a long way of just noting that, as I said before, that if you have a negative exponent here, you flip it over the line so it becomes a to the x power. And just the last thing is, if you have two things here that are being multiplied, a times b to the x power, well, think about it again. If you have a times b to the 3rd power, what do you have there? You have ab times ab times ab, everything being multiplied, and then you, as long as they're being multiplied, you can change the order. So you can write this as a times a times a, which is a cubed, and then b times b times b, which is b cubed, and so that just becomes a to the x times b to the x. And I guess I'm out of room, but similarly, a divided by b all to the x power is equal to a to the x divided by b to the x. So there's properties of exponents, and I think we'll stop right there. In the next lesson, we will talk about the inverse of this function, which is the logarithm.